Hey guys, welcome. And my name is Mr. Kim, and I will be going over the 2025 AP Chemistry FRQ question number 1. I will be going over this as if I'm actually taking the test. This is a special version of a PDF that I made that has the actual spacing that I use for my own students. So let's get started. An incomplete mass spectrum for magnesium is shown in the diagram. It says a percent abundance of magnesium 24 is 79%. The percent abundance of the other two natural isotopes of magnesium, 25 and 26, are approximately equal. Complete the mass spectrum in part A by drawing thick lines in the appropriate locations to represent the percent abundance of magnesium 25 and 26. All right, so the way this looks like is since 24 is 79%, right? 100% minus 79%, that gives us 21%, and that is going to be 25 and 26 combined. Because they're approximately equal, taking the half of that should give us 10.5%, and this is the value that we're going to go for. So over here, 10 is right here. So what I'm going to do is, as the instruction says, make myself a thick line where it's just going to go peak just over the 10% line. Same goes for 26. I'm going to make a line and just let them know that I am peaking just a bit over the 10%. All right, so part 1 is done. I always tell my students to cross out as you go along so you don't forget things. Part 2, describe the difference in atomic structure that accounts for the difference in mass between magnesium 25 and 26. If we look at the periodic table very quickly, we see that magnesium is actually 12 protons, right? So the difference here would be the difference of 13 neutrons for magnesium 25 and 14 neutrons, right? So they have a difference of 1. So what I'm going to do is I'm going to go over to the section right here, and I'm going to write for 1A, I'm going to write I. It's going to be, please see the diagram. And for our part 2, right, we will say that magnesium 26 has 1 more neutron than magnesium 25. Okay, so part 2 is done. And let's go back. So this is done. Let's go on to the next page. Student prepares a 1.85 times 10 to the minus 3 molar solution of magnesium nitrate in beaker 1 and 2.8 times 10 to the minus 4 molar solution of sodium hydroxide in beaker 2 as shown. The particle diagram shown represents a magnesium ion Mg2 plus in beaker 1. A sodium ion in beaker 2 has a weaker attraction in water than Mg2 plus does. Explain this phenomena using Coulomb's law and each of the following. So relative charge of the ions and relative radii of the ions. Okay, so let's take a look. So Coulomb's law is essentially is like this: the force of attraction or repulsion, right, is really a function of Q1 times Q2 over R squared, right? So these two are charges and that's radius. So I know that for part 2, I'm going to be addressing the denominator of this, right? But let's look at the first one, relative charge of the ion. So we know that when two charged particles are larger in charge, they just end up creating more force. Or conversely, if the two charges are smaller, or if 1 point charge Q2 is the same and the other one is smaller, then it'll also result in a smaller force. So let's look at sodium and magnesium. Sodium plus and magnesium plus. So I'm thinking on paper right now, and if we look at the two, then what do we notice? Sodium has a atomic number of 11, right? So sodium has 11 protons, and sodium plus is going to have 10 electrons, like so. whereas magnesium is going to have 12 protons in the nucleus, and it's going to also have 10 electrons because they're going to be isoelectric to, I believe, neon, right? Yep, it's going to be isoelectric to neon, right? So what does that mean? That means that you got 10 electrons and sodium is actually pulling it's got a 11 protons and 12 protons. That means that essentially in the end, magnesium versus water versus sodium versus water is going to be such that magnesium is going sodium let's see, explain it to has a weaker, explain this part. So you can explain it either way. So magnesium has a stronger charge at +2 than sodium's +1. So therefore, that's like saying if this is water, Q2 is water, Q1 for magnesium would be +2, Q1 for sodium would be +1. Therefore, magnesium is going to have a larger value, hence stronger attraction, and sodium is going to have a small value. So let's go ahead and write that down. All right, so oops, sorry. That's not what I want to do. All right, so just going to try to use page down, but it didn't work. All right, so let's go here and let's answer this question. So this is going to be BI, right? So number one, letter B, and it's going to be I. And you're going to say, what are we going to say? Say, according to Coulomb's law, right? So sodium plus, right, has weaker charge, right, at +1, then magnesium, right, 2 plus, right, which would have a +2 charge. All right, so one way to explain this is that because of that, magnesium 2 plus will create a larger attraction to water molecules. Okay. So, okay, so I think that's enough. We could go into it a little bit more detail, but I think we'll leave it at that. Let's go talk about the radius, right? So if you talk about the radius, I don't know why there's a writing there, right? Oh no, this is the one, right? All right, so relative radius I of the ions. What do we understand? So going back to the sodium and magnesium, we understand. So let's see, sodium has a smaller radii and magnesium is a larger radii. So let's look at how that works. If I'm sorry, I got that mixed up, right? Because what happens to the radius? Radius goes large here. Radius looks like this, right? Like that, going across a period from left to right. So the radius is actually smaller and then larger that way. All right, so if you take a look at that way, then what do we know? Sodium has a larger radius than magnesium. And the other thing that we need to talk about is because magnesium has they have the same shielding, right? They're essentially shielded by what? The same number of core electrons. So therefore, magnesium is going to have, so in the absence of different electron shielding effect, the more protons of magnesium is going to actually pull the electrons closer to itself, right? Because electrons are going to be pulled tighter by 12 positive protons in the nucleus than the 10 electrons that's being pulled by 11 protons in the sodium, right? So let's go fill that out. So let's go here and say that in terms of radius, right? So for part 2, right, we're going to write that both Na plus and Mg2 plus have 10 electrons, or say isoelectric to neon, right? However, Na has 11 protons, while Mg2 plus has 12 protons. Both have the same electron shielding. Therefore, Mg2 plus will pull its electrons closer, creating a smaller radii. Okay. And then what do we know is that according to Coulomb's law, force is it's an inverse function of the square of the radius. Thus, Mg2 plus with a smaller radius will exhibit a stronger effective nuclear charge. Okay. All right, that's B2. Let's keep going. So B1 is done, B2 is done. Calculate the pH of the solution in beaker 2. Let's look at beaker 2. Beaker 2 has a sodium hydroxide concentration of this. So let's go solve it, okay? So I'm going to go here, and this is going to be 1C. All right, to solve for 1C, what do? I'm going to leave some space here, and it says to solve for pH, so I'm going to say pH is equal. This is a thing that I tell my students to do. All right, so let's take a look. We know that the concentration of sodium hydroxide is going to equal the concentration of hydroxide because we know it's a strong base, it dissociates completely, and it's monoprotic, right? So that was given to us as 2.8 times 10 to the minus 4, I believe, right? Molar. All right, so now what? We can go with our POH. POH is equal to negative log of 2.8 times 10 to the minus 4, right? And what does that come out to? That's going to come out to 3.553. The reason is because, remember, the number of significant figures, it's 2.80, sorry. So the number of significant figures, which is 3 in this case, is going to be equal to the number of decimal places. Remember that when you do logarithms, right? So that's going to be the POH, right? And then how do we get to pH? pH is pH plus POH. We know that 25 degrees centigrade is 14. So therefore, pH should be equal to 14 minus 3 point, oh, sorry, should be equal to 14 minus 3.553, which should come out to 10.447. Okay, so I'm going to put 10.447 here, and I'm going to circle that. All right, so let's go take a look at the next question, which is asking, hold on, that's done. Let's go to D. For part D, what do we got? Part D, it says a student combines 35 milliliters of 1.85 times 10 to the minus third molar magnesium nitrate with 50 milliliters of 2.8 times 10 to the minus 4 molar sodium hydroxide. As shown in the diagram, calculate the magnesium 2 plus after two solutions are combined, but before any reaction takes place, so no reaction. Assume that the volumes are additive. They literally just gave it away for us, right? So let's take a look. In order to solve this, right, what do we need to do? Well, we need to know that we essentially need to figure out the number of moles of magnesium, which is the only sources right here, right? So we need to figure that out. That's pretty easy. And then we need to figure out the total volume, which is also pretty easy because the total volume is the sum of these two. So let's go solve this one. So this is 1D. C. Let's go to D. Let's go to the next page. All right. So let's go to, sorry, 1D. Okay. So we're solving for the concentration of magnesium 2 plus. So I'm going to do that so that I leave myself a blank here. All right, so let's go solve this. So we got to solve for the number of moles of our magnesium 2 plus, right? And how do we get that? We get that by taking the 1.85 times 10 to the minus 3 moles, right, of our Mg, it's a nitrate, right? MO32, right? And then that's over, right? 1 liter, moles per liter, so that's going to be moles per 1,000 milliliters. Okay, and we know it's 35.00 milliliters, right? That's from the problem. So completely not necessary, but technically speaking, if you do that, you do still have to, I guess, you don't have to show it, but 1 moles of magnesium nitrate should carries 1 mole of magnesium, right? That's only for the units, right? So if you do that, then what do you end up with? You get a, I believe, 6.48 times 10 to the minus 5. That's moles of our magnesium 2 plus. So you're going to get a point for that. All right, next, you have to figure out the total volume. Total volume is equal to, what was that again? 35 and 50 milliliters. It's 35 for sig figs plus 50 milliliters, which gives you 85.00 milliliters, right? And to solve the new concentration of our magnesium 2 plus, it should be 6.48 times 10 to the minus 5 moles per. Now, this is in liters, so we can just do the conversion here, right? So it's going to be 0.08500 liters, right? And what does that come out to? That gives you 7.62 times 10 to the minus 4 molar. So that's 7.62 times 10 to the minus 4 molar. Do that so the reader knows where to go. All right, so next is letter E. Let's go to letter E, right? So I'm going to cross off D. That's done. Let's go to E. For letter E, the dissolution of magnesium hydroxide is represented by the following equation. Magnesium hydroxide goes to dissociation, and then you get KSP equals 5.61 times 10 to the minus 12. Write the expression for the solubility product constant KSP. That's mighty easy, right? So essentially, it's going to be what? It's only going to be the dissociated products, right? Or solubility products. All right, so let's go get that done. 1E, right? 1E, it's going to be KSP is equal to what was that? It's the dissociation of magnesium hydroxide. I'm just gonna write it here for a second because I know that when you guys took it, you guys took it hybrid, which means that you couldn't flip back and forth. So my students told me that they had to write it. So I'm gonna do the same thing, right? All right, so when you do that, when you write it down, what happens? You understand that that's gonna be Mg2 plus, and then that's gonna be hydroxide, except the coefficient is going to become an exponent, and I'm going to circle that. Okay. All right. So let's go back to now that's EI, right? Am I right? Yes, it is. EI2, after the two solutions are combined in beaker 3 is described in part D, but before any reaction takes place, hydroxide is 1.65 times 10 to the 4. All right. So hydroxide is 1.65 times 10 to the 4. Using your answer in part D, which is the what? What was our D? For D, we calculate the concentration of our magnesium, right? Calculate the value of the reaction quotient Q. All right, so this is pretty easy too, right? So let's go. And then you're going to write down here for E that this was for I. So for that, let's solve it. So we have so it wants us to solve for QSP or Q. So I'm gonna write down that. And then we have the hydroxide concentration, which is given to us, I believe, right? Is that the one that's given to us? Yes. So that's given to us, and that's gonna be 1.65 times 10 to the minus 4 molar. And then we have the magnesium 2 plus from part D, and our answer was, what was our answer? Darn it, 7.62. Was that correct? 7.62, right? Yes. So it's 7.62 times 10 to the minus 4 molar. Okay. Plugging into our KSP or QSP expression, right? QSP is equal to, it's going to be magnesium, which is 7.62 times 10 to the minus 4 times our hydroxide, 1.65 times 10 to the minus 4. It's going to be squared. Sorry, my palm reject is not happening so well on my computer. All right, so you have that. And then what's the answer? The answer should come out to 2.07 times 10 to the minus 11. Okay, so 2.07 times 10 to the minus 11. Okay. Okay, and then that's the Roman numeral 2. Let's go to Roman numeral 3. Roman numeral 3, what is that asking for? Excuse me, come here. Okay, 2 is done. Using the reaction quotient Q, predict whether precipitate should form as a mixture in beaker 3 approach equilibrium. Justify your answer. Now, we need the KSP, which is 5.61. So let's go. So we're going to compare QSP to KSP. So when you go over here to E3, right? We're going to have two values, right? You have Q, which is equal to 2.07 times 10 to the minus 11. And you have your KSP, which is, what was that, 5.61 times 10 to the minus 12, right? So we know, and it says to justify, right? So we know that in this case, Q is greater than RK. What does that mean? If Q is greater than K, that means at condition Q, we have higher concentration of our products. In this case, the magnesium 2 plus and our hydroxide, right? So what does that mean? That means we have too much dissolved ions, which means it's going to drive, it's going to go to the left in the equation, and it's going to start precipitating out. So the answer would be precipitate should form because QSP is greater than KSP, which means we have greater concentration of our products than at equilibrium. Okay, and that's our answer. All right, so that's our E3. Let's go back and check that off. All right, so E3 is done. Final question. F, in a separate experiment, student adds nitric acid to decrease the pH of a saturated solution containing undissolved magnesium hydroxide. Does the amount of undissolved magnesium hydroxide increase, decrease, or remain the same? All right, so what are we adding? We're adding protons, essentially, which means it's going to react with what? It's going to react with this guy, right? So what's going to happen if it reacts? Well, it's not going to react with this guy. It's going to react with the dissociated hydroxide, right? So let's go make that happen. So, okay, where are we at? Okay, so let's go to 1F right here. Question 1F, right? And what do we know? The amount of undissolved, right? See, so we know that the amount of undissolved magnesium hydroxide will decrease. So you always want to start your answer by stating what they're asking you to figure out, right? As the proton from HNO3 will react with the hydroxide ion from magnesium hydroxide dissociation, right? Now, we say that hydroxide ion is a product of dissociation. And according to, I'm going to talk about, that's right, Le Chatelier, removing products, which is OH minus in this case, will cause the reaction to proceed to the right. Okay. All right, so that's 1F, and I know you're thinking, hey, why are you going back? Because too many of my students forget to answer a question, so I tell them when you're done, go and cross it out. So that is the end of question 1. I hope this was helpful to you, and thank you for watching.